This is PeerConf. This is day 3 for all of you watching on YouTube. We're about to start the unconference portion of the day. It's 10:15 a.m. here in Chicago. We're going to talk about the technology and psychology of refactoring this morning. How are folks feeling? Day 3. Good? Everybody's had their coffee? Or tea. We don't drink shame here. Don't yuck somebody's yum. Hi, folks. My name is Chelsea Troy. My pronouns are she and her. They or them is also fine. Today, I'm going to talk about refactoring. I don't think this talk requires any content warnings, but if I missed something, I'd like to hear from you afterwards. And in general, I'd love to hear your feedback on this talk. You can reach me at chelsea@chelseatroy.com. My hope is that I can provide something for everyone today, designers, product managers, and developers alike. There will be some code in this talk, but not a ton. There'll also be a number of things about dealing with the product and dealing with other people who coordinate with your team. So we'll cover some technical level details for the software engineers in the crowd and some operational details for product managers. So let's start here. What is refactoring? Can I have a show of hands? Who has done a refactor before? Okay, most of you. Okay, how many of you love refactoring? A few hands. How many of you hate refactoring? I see a couple. Maybe some product managers, maybe? I see a couple. Okay, so if we've done it and we have opinions on it, we definitely know what it is, right? It's kind of like one of those, I know it when I see it things, maybe? So there are a number of canonical definitions, and they tend to coalesce around this idea that refactoring is changing the design of existing code without changing the user-facing features. How do I, okay. Changing the design of existing code without changing the user-facing features. I don't love this definition because it comes with 2 assumptions baked into it, specifically into the term user-facing features. So let's talk about user-facing features. First assumption, who is a user? Refactoring changes the developer-facing characteristics of a code base, and developers are users. You can almost hear the designers in the crowd wincing at that right now. So let me address that. It's true that in many cases, code design is, and it should be, secondary to the software's functionality. If the only way to write the feature that the end users need is messy code, then you gotta write the messy code, and that's life. Because if the software doesn't work for the end user, it does not matter how beautiful the code is, so it won't be used. It's also true that if the code is illegible, the software will very quickly not work for the end user because developers will have a hard time understanding it and they'll be afraid to touch it. So updates will take too long or they'll even become impossible. No designer wants to hear that a tweak to the animation is going to take 2 weeks, right? So we keep code in a maintainable state to minimize that kind of wait time for designers, developers, end users, product managers, everyone. Okay? There's another assumption baked into the term user-facing features. What is a feature? So we tend to equate user-facing features to content and navigation features, buttons, tabs, text, pictures, requests, that kind of thing. Sometimes we call these features functionality. We'll call them content and navigation features here. There are other kinds of features. Other kinds of features include scaling. Does the software work when a lot of users are on it? Does the app work when the network connection is heavily taxed or poor or non-existent? Robustness. Does the software respond gracefully to unexpected input from users or from network calls? Security. Does the software keep users and data safe when hackers try to compromise it? After all, not every unexpected input is unintentional, right? Accessibility. Does the software work for users who use screen readers, large font, high contrast UIs, loud and clear sounds? Does it work for users who have compromised motor control, compromised dexterity? Okay, inclusion. Does your computer vision app work for people with darker skin? Does your software only ask questions about user sex and gender if it absolutely has to? And if it absolutely has to, does it ask those things in the right way? If your software has anything to do with bodies, does it work for all different body shapes and sizes? All of these are first-class features, just like profile pages, buttons, and news feeds. And we often refactor specifically to get some of these features, right? Better error handling, better network performance, or better predictive results. But whether we call that a new feature or a refactor isn't clear. By labeling our work as a feature or as refactoring, based on whether users notice a difference, makes some assumptions about who is a user. And we don't have to make those assumptions. Instead, let's imagine that software exists on a continuum toward maintainability. And refactoring is the work that we do to make our code as maintainable as possible. So what does it mean for software to be maintainable, right? We could have a whole conference on that, probably. You could call it Pineapple Conf. Pineapples are the most difficult to maintain plant. I swear. So you know what? I'm the one with the mic, so I get to decide what maintainable means today. And I'm looking for three things specifically, and I'd like you to think of them as constant works in progress on a software project. So this isn't a binary, it has it, it doesn't have it. These things are constant works in progress. Refactoring is the thing that we do to give our software more of these things, to move them on this continuum of having this and not having it. We want software, first of all, we want software to be collaboration friendly. How can other technologists maintain this code together? And this is the thing we most commonly associate with the term refactoring, because we want to leave the code clean and organized so that other developers can figure out what it does and why. So who does this well? I have a few examples for you. None of these examples paid me to talk about this. They're projects that I've worked with. So the first one is the Spring Framework. Spring Framework makes really exemplary use of documentation, rigorous tests, thoughtful syntax, and thoughtful architecture choices keep the code legible and thoroughly explained so that their distributed team and outside contributors can understand and improve the way it works. This project is open source. Highly recommend taking a look at it. Their team is distributed. They're all over the world. They have to keep the code in a maintainable state because people are working on it and they're not all working on it at the same time. And so they can't necessarily always talk to each other. Got another example for you. This is Apple's programming language, Swift. Swift aims to enforce some collaborability on Swift projects. Swift is a compiled type language. Show of hands, who's written Swift? Do I have any Swift writers? A couple Swift writers. Okay. So this language, it leans on optionals and it includes a lot of features to ensure the safety and legibility of the code written in it. At this point, it's influential enough that the folks developing the next version of Java look at Swift for inspiration for how the next Java feature should shake out. And you can see their commitment to concise, legible code in the source, which is also on GitHub. Swift is also open source, so I would highly recommend taking a look when you get the chance, if you get the chance. Okay, so we want software to be collaboration friendly. Can we agree on that? Yeah, okay, nodding, good. I hope we can, because I already wrote these slides. We also want it to be dialogue friendly. So this one's a little tougher to pin down. By dialogue friendly, I mean, how does a user or developer share their expectations about this program? So the feedback cycle is a really important part of software development. So if we want to develop maintainable software, that software has to merit maintaining by being used. And in order for software to be used, we need to make sure that it keeps up with what users and development teams expect it to do. So how do we do that? There are a couple ways. Well, when we deploy apps, we might do user testing, right? Your typical design cycle. Sometimes if it's a mobile app, maybe we use App Store ratings to get information about how our project is doing. If we have developers who are users, maybe we go on Reddit and spy on what they're saying about our software. So Google's products often do a really good job of providing mechanisms for users to share how their expectations differ from what they get. These are some dialogues that I pulled out of Gmail. I was using Gmail and I needed help figuring out how to do something. And so I got an article that told me how to do the thing I wanted to do. And at the end, you see these two buttons. Was this article helpful, yes or no? If you click no, you get this text box that asks how it can be improved. And this is really impressive to me. I think that this really helps software stay up to date on what users are expecting. And I pity whoever has to read these because people only type in this when they're angry, right? But it's a really helpful feedback mechanism for folks to figure out what the software, what users are expecting the software. So software that fails to open this dialogue, it ends up getting out of touch with user needs and then it becomes shelfware. Sad face. The third aspect of maintainability, can y'all still hear me okay? The third aspect of maintainability is resilience. How does the code react to unexpected or unideal inputs? A resilient app anticipates the things that a user could do, and it reacts gracefully, even when something happens that it didn't anticipate. When software isn't resilient, we end up with failures where the software is clearly not working as intended, or where the development team didn't foresee that something could happen. I once worked on an app for ramp agents working on the tarmac at airports. It scanned luggage, pets, mail, military equipment, hazmat, hazardous materials into the holds of commercial airplanes. So no pressure. So we built this beautiful app, these API clients. They made calls to the server in real time every time you scanned any bag, and they returned updated information about the whole flight, calculated on the server. With each call, you could figure out if the weight was balanced correctly and all of this. We were very proud of it. We sent it to user testing. The product owner came back to report that ramp agents spent about 10% of their time in the app scanning bags. 10% is really low. What were they doing the other 90% of the time? Any guesses? Twitter. Not Twitter. They couldn't use Twitter because what they were doing is they were walking around on the tarmac, which, by the way, is where the planes are, holding the phones in the air like this. Why were they doing that?
They didn't have a connection.
They didn't have a connection, and every single call, every single scan blocked on a connection. I don't like to use the term obviously when I'm talking about software, but in this case, I think it fits. Obviously, that was not going to work for them. So we completely refactored the app. This time, with the question in mind, how much stuff can we do without any network connection at all? We couldn't coordinate scanning between the scanners this way, so we assigned each scanner to a pit in the hold of the plane, and we queued the scanning requests that way. And then we calculated weight distribution based on how many bags had gotten into each hold, essentially. The difference between individual bags doesn't mean so much. At the very end of scanning, the ramp agents needed a network connection to connect to check some security things. So they could guarantee that network connection by plugging the phone into a networked holder called a cradle. Just one time at the end of scanning, not in between every individual scan. We took an existing app that did not do what the users needed, and we worked together to translate that feedback into changes that worked. And this is an extreme example that I chose for clarity, but this happens on a lot of software projects, right? Requirements change out from under you. We write maintainable software precisely so that when the underlying requirements change, our code is ready to change too. Because writing maintainable software means assuming our assumptions will be wrong. Software has to change when it was originally written under assumptions that are not true or assumptions that are no longer true. So how do we hedge against the possibility that our assumptions are wrong? We need to notice and examine our assumptions. As I was developing this talk, Kenneth Mayer asked on Twitter, when is enough refactoring enough? Is Kenneth in the crowd by any chance? Okay, so nobody get on Twitter and tell Kenneth that he is Pearcon famous. Definitely don't do that. His handle is Kenneth Mayer, in case you wanted to. Definitely don't do it, though. So I think it would be helpful to approach this question, when is enough refactoring enough, with an example. Can I have a show of hands? How many of you have heard of dry software engineering? Okay, that's a lot of hands. What does dry stand for? Stands for don't repeat yourself. This is an adage developers learn to avoid duplicating stuff in code. So Coraline, Ada Emke, you'll hear from her this afternoon. She articulates a misunderstanding with this term really well. She explains that the point of dry is to not repeat concepts. It's not referring to individual lines of code. Sometimes it makes sense to leave similar lines of code in several places, because when you extract a variable or a class or a method for them, you communicate the perspective that these two things are the same. And sometimes they're not. Suppose we have a class representing each view in our app. Who are my Java developers? This is Java, love Java. You don't have to love Java. I don't mind Java. So suppose we have a class representing each view in our app, right? So we have a list view and we have a detail view right here. In each one, we need to load the view, we need to handle button taps, and we also need to load this navigation bar at the top so that you can get to different views, okay? Does this premise make sense so far? So we have here both of these views do all of these things, so maybe it makes sense to extract a superclass, right? Let's call it a view. It does all our stuff, and then our list view and our detail view both extend view. So if you call any of these methods on either of these, they will work the way that they do in the view class. Okay, so great. We've got our refactored code. Now we're adding a login page. So we make a login view. And we still need to load the view, and we still need to handle button presses. But the thing is, we don't need to load this navigation bar, because if you haven't logged in yet, then there's nothing to navigate to. So what do we do here? Do we extract a superclass? And then, so we extract the superclass, we have our login view. Do we extend view and then override load navigation bar with a no-op so it doesn't do that? My opinion is we don't do it this way, unless you absolutely have to. We have a couple of other options, right? Do we pull loading the navigation bar out of the superclass and then add it back to the subclasses that are using it? We could do that. That's another option for something we could do. Maybe extracting a collaborator will be a helpful design pattern for us. We have a navigator. It loads the navigation bar, and then our list view and our detail view have that. Our login view doesn't. That's another thing that we could do. Or maybe we make a taller view hierarchy like this, right? You have a view, and then you have a navigation view, and that extends view. And your list view and your detail, they extend navigation view, but your login view, it just extends view. So it doesn't have that navigation bar functionality. Side note, you'll see very tall hierarchies like this in mobile frameworks exactly because of this kind of thing, because mobile frameworks, they do a lot of under the hood stuff for you. And so this ends up, this is very common in Android framework, in Android and iOS. But if you need default functionality rather than like interface adherence or something, and you're working with a language that prohibits multiple inheritance, some of these options are not options for you. We have a rule in software engineering to help us avoid situations like this. It's called the rule of three. Can I have a show of hands? Who's heard of the rule of three? Okay, cool. What is it? It's the rule that code should be duplicated in at least 3 places before factoring it out. Does that sound familiar? Okay. Why? What is it about 3? Is 3 some magic number? I'm getting some nods. No. The answer is no. I'm sorry. I don't want to, I know this is the city of yes and, but the answer is no. We could factor out the navigation bar and get 8 views in and then run into the exceptional class, right? And then we have to decide between the subclass and the no-op or adding the navbar method to the other 8 classes we've already done this with, right? In this case, it's 8. The number's not 3. 3 is a rule of thumb because if we have to do something exactly the same way 3 times, the probability is higher that these things really are the same than if we only have that similar functionality 2 times, right? So how do we judge when to start refactoring and when to stop refactoring? Do I have anybody who's taken like a finance class in the crowd? It's okay if you haven't, we're gonna go over this. So we have refactored enough when we have balanced. This is my scale. Do you like this? I drew this. Okay. We have refactored enough when we have balanced the probability that this thing's going to change times the amount of work to change it with the amount of work that we're willing to do. So when you, in finance, when you multiply the probability of something and the cost of something, it's called the expected cost. So this is the expected cost for us, right? This is the amount of work we're expecting to have to do on this thing. And we're balancing it against the amount of work that we're happy to do, or at least the amount of work that we're willing to do, or the amount of work that we're willing to delegate some other developer to do. So how do we figure this out? We need to ask some questions, right, as we plan how to write our code so that we can figure out what these amounts are. So let's start with the probability, right? How likely is it that we're going to have to change this? Well, maybe we're not exactly sure. There's some things that can help us guess. More examples supporting our assumptions help us guess. The more examples of something we have in the code, the better idea we have of whether it's the same. We've talked about this. What is this? This is the rule of 3, right? That's what this is. So similarly, if we have more customers using our app in the way we thought that they would use it, then it's less likely that we're going to have to change the underlying features, right? Because we have evidence that users are doing it this way. I don't know if do you have like a user rule of 3 or anything like that? Maybe not. Okay. So what else can we use? Well, regular feedback cycles help us. If we have regular feedback cycles to catch and correct differences in user expectations and software requirements early on when they're small before they become bigger, then it's less likely that we're going to have to make large changes to the software later. So this is one question we need to ask. There were 2 parts to that equation, right? The probability that we have to change it and how hard it is to change, right? Okay, so let's figure out how hard it is to change now. How much work is this change? Once again, hard to get a number, right? But there are a few rules that I find useful. First of all, consolidating is usually less work than separating. It's less work to consolidate our views to inherit from a superclass, like we did with Vue, than it is to break that superclass apart again when we realize it represents a concept that's too general for our use case. Refactoring up into a super, it tends to be less work than figuring out how to refactor back down. It's usually less work to change documented patterns than it is to change undocumented patterns. This is important when we're deciding whether to go with system patterns or our own bespoke ideas for how that software should be written. The more commonplace the pattern you choose, the more Googleable it's going to be if your other team members run into issues after you've left or you've rolled off the project or you're busy. This is a reason that I really advocate for people to use common patterns in mobile development, because you can Google your error message more easily. Okay, what else? Well, it's usually less work to change an existing system than to start over. This one's important. Refactoring the scanning app where they had to hold it up in the air to get it to work, refactoring that app was a huge job, huge. And it was still less work than rewriting that app would have been. Even sweeping refactors in your software can save the team down the line from needing to do a complete rewrite. Show of hands, who's been involved in a complete rewrite? It's a whole thing, right? It's a whole thing. It's a whole thing.